Hello, in this video I will demonstrate how to derive Euler's identity. We'll start with a few basic derivatives. The derivative of e to the x is e to the x, of sine of x is cosine of x, and of cosine of x is negative sine of x. The values that these functions take at x is equal to 0 is sine of 0 is equal to 0, cosine of 0 is equal to 1, and e to the 0 is equal to 1. Now let's take a look at what a Taylor series is. So in this case, we'll use a Taylor series centered at x is equal to 0. A Taylor series is basically a way of having an infinite polynomial that approximates a function around a given point. And as we add more terms to the polynomial, the approximation gets better and applies to a longer distance from that center point. So in this case, we have the Taylor series of a function f of x. So we have t of x is equal to the infinite sum of the nth derivative of f evaluated at x is equal to 0 over n factorial times x to the nth power. And we see here that taking the kth derivative of the Taylor polynomial, we get the kth derivative of the function. So taking any derivative of the polynomial, we get the derivative of the function evaluated at the center point, meaning that the Taylor polynomial approximates the function around that point. Using this notation for sine of x, cosine of x, and e to the x, we get these following expansions. Notice that wherever I see sine of x, that goes to 0, and wherever I see cosine of x, cosine of 0, that simplifies to 1. And e to the 0 also simplifies to 1. So expressing these things in sum notations, I get sine of x is equal to the infinite sum of the alternating series, because that's what the negative 1 raised to the nth power represents. So each time I have a new term, it alternates in sign. So the first term would be a positive sign, the second term would be negative, the third term would be positive, and so on and so forth. So for sine of x, I see that wherever I have cosine of 0, which is equal to 1, I have an odd power of x, and wherever I have sine of 0 is equal to 0, I have an even power of x. So all the even powers of x will die off, and I'll only be left with the odd powers of x. So sine of x is the infinite series, alternating series of x raised to the odd powers over those powers factorial. For cosine of x, I have cosine of 0 around multiplying x to the even powers and sine of 0 multiplying x to the odd powers. So all the odd powers of x will die off, and I'll be left with the alternating series of x raised to the even powers over 2n factorial. So where 2n and 2n is an even number. And for e to the x, all e to the zeros are 1, so I'm simply left with the infinite sum of x to the n over n factorial. Applying to the ratio test to these series, we see that they converge for all radii, so we have an infinite radius of convergence, meaning that we could basically set these functions equal to the series. And using this, we have a polynomial that represents our functions. Now let's substitute e to the I theta for e to the x, and plugging that into the series, we get the infinite series from n is equal to 0 to infinity of I theta raised to the nth power over n factorial. I times I is negative 1, I cubed is negative I, and I to the fourth is positive 1. So expanding all of this out, we see that wherever I'm multiplying theta to an even power, the i's cancel out, but it still alternates because I repeats every fourth power and even numbers repeat every second power. So I have an alternating series of theta that even powers over those powers factorial. And where I'm raising theta to an odd power, there's an I term that survives. It still alternates in sign because I to the first is I and I to the cubed is negative I. So those terms still alternate, but I have an I left over. So for odd powers of theta, I have the I on the outside of the sum multiplying the entire sum, so the infinite series from n is equal to 0 to infinity of the alternating series of theta to the odd powers over 2n plus 1 factorial. And these are just the series for cosine of theta and I sine theta. So we could rewrite this as e to the I theta is equal to cosine theta plus I sine theta. And this is Euler's identity. A special case of Euler's identity is when we use the angle pi. So e to the I pi is equal to cosine pi plus I sine pi. And cosine of pi is equal to negative 1 and sine of pi is equal to 0. So rewriting that, I have e to the I pi plus 1 is equal to 0, which is a famous and special case of Euler's identity. Taking a look at the complex plane with the imaginary axis on the y-axis and the real axis on the x-axis, we could see that instead of writing z, which is a complex number, any complex number could be expressed as a plus I times b, where a and b are real numbers. Instead of expressing a complex number as a plus ib, I could write this as r times e to the I theta, where r squared is equal to a squared plus b squared, and tangent of theta is equal to b over a. This makes multiplying and dividing complex numbers a lot easier, because instead of messing around with conjugates, I could divide the lengths, which is r, and rotate the angles, theta, because when you divide an exponent, you get e to the I theta 1 over e to the I theta 2 is really just e to the I times theta 1 minus theta 2. So the angles would change by rotation. So this gives a nice way of visualizing multiplying and dividing complex numbers, because I can just simply multiply or divide the lengths and then rotate the angles. And that would be how you multiply and divide complex numbers, which would be a lot more intuitive to understand than multiplying by a1 plus ib1 times a2 plus ib2 and distributing all that out, or in the case of division, you would need to use conjugates.